All right, so we'll start with number 11, with the friend dropping an apple on you out of a tree. And so this one actually, I would say your why should involve probably some text, but also energy diagrams, because this is more, the first half of this one is about conservation of energy, and the second half is about impulse. So I'm going to do an energy diagram, but I probably also would add some text down here about something like you apply an impulse to catch the apple. So this one combines both conservations. So when the apple's up in the tree, what type of, that's our before situation, our initial, then we have the during, and then the final is just before you catch it. So what type of energy would it have when it's just hanging out up there in the tree? Potential gravitation. Would it have kinetic? No. Okay. So we probably should add a potential grav here. P grav. Any other types of energy that we think would be going on besides gravitation and kinetic? No thermal, or there's not a spring attached to the apple, or a bird, or anything? Okay, I agree. So, and at the beginning of this, when it's up there in the tree, and it says it drops, says a friend climbs an apple tree and drops. What is implied by drops? Someone demonstrate to me, show me something dropping. Okay. What did it? How? What was its characteristic just as you dropped it?
There's an motion.
It wasn't moving, right? Because if I drop it, I mean I just let go of it. If they say threw down to you, then it would have an initial velocity, or threw up and then down. But dropping implies starting from rest. Okay? It's kind of one of those nuances in our wonderful English language. So it's not going to have any kinetic energy when it starts. It's going to have, let's give it a bunch of potential energy grav. And then I don't think there's any work done on it as it drops. No external work, just the interior work done by gravity. And so our final system energy has to equal our initial. Where are we going to, how much potential energy grav we're going to say it has just when it hits the hand? What do you want to say? None. Let's say none. Because we can set 0 anywhere, right? Why not set it at the hand catching it to make life easier? So that means that all of that energy here has to go to kinetic energy. All the potential grav goes to kinetic. Yay! That tells me how to set up my problem, right? It tells me that the potential energy grav before equals the kinetic energy afterwards. And then I just remember my equations, which are mgh for potential energy grav and 1/2 mv squared, speed squared for kinetic energy. Maybe it'd be good to look at what the problem asks me to find. The speed of the apple just before you caught it, and it's 0.22 kilograms and 3.5 meters is that height. So, oh, but the m's cancel out. Oh, gh 2gh equals v squared. Oh, I can find v, right? How do I know what little g is?
Oh, it's because it's like,
How do we know it's 9.81 units per kilogram? Well, we can find that by energy, but how do we know that that applies to this problem? Because it's on Earth. How do we know it's on Earth? Because it's on trees. The only planet we know of that has trees is Earth. So kind of, it's one of those nuanced things again. There's a tree and an apple, pretty good assumption it's Earth. Right? Yeah. If it's a rock falling off a cliff, maybe it's not Earth. Oh, so and then I can, on H they gave me, now I'll tell you what the most common mistake in getting to V will be. Getting the square root. So what I would suggest is write an intermediate step here. Write what V squared is. And then write what V is. A lot harder to forget the square root if you actually build the written step in there. Okay? And I know you guys can all do the math, right? Yeah. When you catch the apple, which is what I'm about to go on to. So, the second part of this is you catching or stopping the apple. And that's the momentum part of this. So I have to change the momentum of the apple, I need to apply an impulse to it. And that impulse is going to cause the momentum to change. Momentum is going to go from some value down to what when you catch it? 0. So I have to apply enough impulse to cause that big of a change in momentum. So I'm going to use my equation that says the change in momentum equals the impulse. And this would be momentum mass. Oops, let's go one more algebraic step. This would be momentum final minus momentum initial. And this would be force delta time. These should actually all be vectors like that. But we said my final momentum is, we're going to step. M times V final minus M times V initial equals force delta time. And I know that my V final is 0, so this is 0 minus whatever the mass is they gave me, 0.22 kilograms. And then my time, 0.28 seconds, 0.28 seconds. And I'm going to come out with a negative answer. This should actually be negative force. Because if I'm taking down as positive, yeah, that works. And I'll get an answer for force. Huh? Your answer from A? All right, so part B here, what we should have done a force diagram. That would have helped us avoid not including this. So here's your apple, here's your hand, right? The apple, of course, has mg down, and you've got to put a force up on it. Well, that force up is going to be the force to stop it. Let's call that F sub S. That's the force that to apply the impulse that takes away the momentum. But what if it wasn't moving? Do you still have to apply a force to the apple? I don't know. Put something in your hand. Are you applying a force to it? If you're not sure, try something heavier than your phone. Try it with your water bottle. Are you applying a force to it? Yeah. So, F here is going to be, and this is from, say this. So we have F minus mg equals 0, but F, so this is going to be this should be Fs. I can't write the minus 0, sorry. Because it's actually, in this case, it's not equal to 0. I'm trying to avoid acceleration here. So the force that you have to apply is going to be the force to stop it and the weight of it. Okay? Because think about if you just had it there, you'd have to provide the weight. But it's coming downwards, you need to apply a force to create this impulse. Therefore, you have to provide more force. So whatever you get up here is your stopping force. And then, of course, mg, you know how to do mg. Right? So that's why you kept getting it wrong. All right, so on to number 13, which would be good if I showed it to you. There it goes. You got a block of wood, rests on a rough surface. As soon as I see the word rough, I think, oh, friction. Not like rough. Friction. And bullet strikes the block with this speed and embeds itself. Oh, that's a perfect, if it embeds itself, it's a perfectly inelastic collision. Right? Because two objects become one object. Also, I know momentum's conserved during that, but kinetic energy isn't. And the bullet block system slides this far before coming to rest. Oh, so if it slides, that means friction is going to oppose that sliding, and it's going to do work on it. Oh, that's way back. And that's what's going to make it come to rest. So we kind of have the reverse of what we were looking at last time. Last time we looked at energy and then did momentum. Here we got to start with momentum and then end up with energy. So in the Y of this, I might actually do both my before, during, and after diagrams and a bar graph by the ideal situation. Because the momentum is going to be conserved in the collision, but the friction does work to stop the block. Stop block slash, what do they call it, a bullet? Bullet. Bullet. Common mistake will be to forget the mass of the bullet when you're looking at the block and the bullet moving together. All right? So, my before, during, and after is going to be just for the collision. So I'm going to have the block with the bullet, the block with the bullet touching, and then the bullet before it hits the block. And before, I'm going to call that the momentum of the bullet, BUL. During, there'll be an impulse on the block and an impulse on the bullet. And afterwards, there'll just be the momentum of the bullet and the block, which I'm going to label BB. Oh, someone had that like it's one of their example problems, right? Yeah. I would also do a bar graph here for this one, though. Freehand sketching it. I'm going to have before, during, and then after, but this is energy. So beforehand, I would have a bunch of kinetic energy. I would have negative work by friction, and then afterwards I'm going to have nothing left. I know, not a very pretty bar graph, but so I need to do the momentum part of this first. Then I can do the energy part. What does it finally want me to come out with? The coefficient of kinetic friction. Oh, this problem is nice. It incorporates everything. Okay. Well, you know, you always like to put these type on the test, right? Incorporate all the skills. So, momentum of the bullet has to equal the momentum of the bullet and the block together. So this would be mass of the bullet, velocity of the bullet, and since those are both positive, you know, all the velocities are that way, we'll label all as positive. This would be mass of the block plus mass of the bullet, and the velocity of the block and bullet together. I think they give us all those, don't they? Yeah? So you can solve for the velocity of the bullet. Because they give us the mass of the bullet, they give us the initial velocity of the bullet, they give us the block and the bullet's masses. Yeah? Then, tackling the energy part, the kinetic energy plus negative work due to friction is going to equal 0. I can rearrange that to make myself happier. So I have all positives, right? One half mass of the bullet in the block, speed of the bullet in the block, equals the frictional force times how far it went. And I know everything except the frictional force. And actually on the test, this is where I would have you stop. I'd have you find the frictional force and be happy and done. What this question asks you to go one step further, which is to recognize that the frictional force is mu force normal, which we talked about, but we're not really doing many problems except for this one with that. And so you have the frictional force. You're looking for mu. The force normal is going to be the mass of the bullet and the block together times little g. It's going to be the weight of the bullet and the block. Because if the block's just sitting on the table, right? It's got its weight down, MBBG, and a normal force up. Let's go to this answer. What is this? Golf. Yeah, that'd do it. So the green part is the part that you're doing for this problem only. We're not really doing as till a unit or so from now.
Did that say bullet? Or...
Where? Here?
Yeah.
Bullet block. As soon as you're past that initial momentum, everything's the bullet of the block together.